Today we continue to work on our small project where we render images in a specific way using quads, which are part of a quad tree. As in previous part, let me show you the final result that we're trying to achieve. We have a program running, there is an image loaded, and with our keystrokes, quads are being split into smaller quads. An average color for each quad is being calculated, and the image takes a nice artistic look. Last time we managed to set up the rendering pipeline. We are now able to load the image and render it, and today we're gonna jump into the quads part. The quad tree data structure is not that relevant in this particular project, but we're using quads which are somewhat related to it, and if you read this article you will understand much better about the data structure itself. But what we are interested in is a quad that is represented by some rectangular area, and we can then split it into 4 similar smaller size quads and then split it further, and thus receiving some interesting effects on our image. So let's jump straight into it. This is our main C when we left it as we left it in our previous episode, and today we're gonna start with defining our quad structure. So let's define what our quad is going to look like. So each quad is referencing some source image, so we will have image. Let me open main, let me grab this image and move it into quad. Then this one will require quad import. This requires the int. Alright, so each quad is referencing the source image, and in our case this source image is always the same, but it kind of simplifies things when we actually need to recalculate things based on the source image. Each quad has a boundary, so let's think what a boundary is in our use case. Boundary is simply some box and an area of the box, and the box is very simple structure saying that, hey, I have left, right, top and bottom coordinates. So this is like a rectangular area. Next, given a source image, we would like to calculate an average color based on the source image. Average color, let's define that. Average color is going to be simply color and some error. As we're calculating some average color, we will also calculate some standard deviation, which will tell us how the pixels in this rectangular area differ from the mean value that we calculate. We don't really need the exact value, we simply need it to compare to each other, to compare quads to each other. So the higher the error value, it indicates that the pixels vary more, and it benefits us to split quads with higher error rate or higher error value. And now we need to define the color structure, which is as easy as bite-sized red, green, and blue. And finally, we need to be able to split a quad, so it will have some children if and when we have split it. So we need to define structure named children, and each quad is always split into 4 quads. So it's going to be top left, top right, bottom left, and bottom right. 4 quads. Now our compiler is complaining because we have this recursive structure where quad needs children, children need quads. So we need to make some forward definitions saying that, hey, I will have some struct children, so that this quad knows, okay, there is struct children available somewhere. And we also need to say that, hey, type def struct children as children, so give it a name for the struct. And this one now complains, and yeah, we need to say that this is actually struct children. All right, so this is pretty much it for the quad, what it represents. Now we must think like what methods we will use. Initially, when we load an image, we will have a single quad which covers the whole image area. So we will create quad init from image. This is a function that will receive some image and construct an initial quad. And then each quad should have an ability to be split. So we will have some function that will return pointer to children saying, hey, please quad split me given some quad. Now we can create our implementation file, include the header, and start thinking how we can implement this. So let's start with initting quad from image. We're gonna return a structure quad where we have an image which references our image. I think we need to tell it that this is going to be const. We will have some boundary. We will have some average color. And our children is null pointer because we haven't split it yet. Let's see, what is a boundary in this case? Alright, so it's going to be a box, and its area is going to be box area given this box. Quickly, let's do the box area, which returns, I think we defined it as 64-bit value given some box. It is as simple as saying that, hey, box right minus box left times box bottom minus box top. Right, so it calculates an area. It is not going to be used in this episode, but we will use it next time, as we will use it in when we select next quad to actually split. Right, so the box. The box is simply left, which when we want to cover the whole image starts with 0, same as top, and then right is going to be image width, and bottom is going to be image height. So the only thing left is average color. Average color is something. To calculate an average color, we need to first know the histogram of the image, or particularly of the box or the area of the image that this quad is covering. So we will say that it's going to be color from histogram given some histogram, and histogram is going to be some sort of an array of counters for each color, so it's going to be times 3. So histogram is an array of counters for each color, for red, green, and blue. Each of those colors, for example red, can be represented as a single byte. So that means values from 0 to 255. And given the whole image, or at least like its boundaries, we want to know how many times a value of, let's say, 13 red happens, or we see that value in the image. We need to make sure that all the values initialize to 0, and then we need to like calculate histogram given an image, given our box, and given our histogram where we're going to put the results. Let's see. So how do we define calculate histogram? It's going to be image box, and it will have a counter histogram static. So it kind of says that, hey, that we want to receive an array which has a minimum length of 668. So sometimes the compiler can help there, sometimes it doesn't help, but it's a good thing to write it out here. All right, so how do we calculate histogram? We need to iterate over the whole image. Right, so image is int, so for int row from 0 up to image height, column from 0 up to image width, we're gonna fetch the red value, the green and blue, and then we can say that, hey, histogram for red, increase it by 1, histogram by blue, and histogram by green and blue. But the thing is, like, histogram keeps track of counters for all 3 colors, and those colors have offsets. So red is offset from 0 to 255. Green is actually starts with 256, that's the offset. So it will have from 256 up to 511, and this one in this interval. Right, so let's say we read some pixel value or GB. Red is like 13, green is 100, blue is 200. We update the counters for red, for green, for blue inside a single histogram, and we're using offsets. Here it's like 0 plus. The offset for red is 0. For green it's 256. We know that red, which can be from 0 to 255, will never end up in any of these intervals. Same for green, same for blue. So what is left is how do we grab these? So it's going to be image data. Again, it's going to be a row time image width times 3 plus column times 3 plus 0. This we can delete, and this plus 1 plus 2. So in our previous episode we already calculated how we can offset image data. So image data is pretty much raw byte data. We know the width, the number of pixels in an image in a single row. When we load the image, each pixel is loaded at 3 bytes. Each byte represents a color, RGB. So to actually access the value inside of like row and column, we need to first skip this amount of bytes. So number of rows, each row is represented by image width times 3. And then we access the column, of some value, and each column pixel is also represented by 3 different colors, red, green, and blue. And finally, when we're at correct index, we know that red comes first, the next byte +1 is green, and next byte, so +2, is blue. The problem here is, of course, that we have neglected the box. So we currently have histogram for image, and we're going to be like calculating always for the full image. But what we really want to do is to restrict the histogram for the box. And box is restricted to some rectangular area of the image. It can fully cover the image, but it can also represent a smaller area. So the row is actually going to be starting with box left. Row is going to be left, then box right. Oh no, it's actually a row. That means it starts with top and bottom. Column is going to be box left and box right, and everything else remains the same. So these are units. And this is how we calculate histogram for specific rectangular area of an image. Once this is calculated, we need to calculate an average color of from this histogram. Let's see how we can do that. Average color from histogram. We receive histogram static. Now histogram, again, I'm repeating myself, contains counters for all 3 colors, red, green, and blue. So we need to calculate some sort of weighted color red from histogram 0, green and blue, given their offsets. So this weighted color function is actually weighted color. It's going to work with counters for only one specific color. So we want to have it 256 values only. So let's define what this weighted color is. Type def struct weighted color is pretty much an average color value with some error, right? So knowing the histogram of red, we need to calculate the average red value. Knowing the histogram for green, we need to calculate an average for green. And of course we also calculate their deviation as well. Once this is done, we can calculate the overall error in, I think, like Grayscale, and then we can return an average color where we say that, hey, color is actually color and error is going to be error. So red is going to be red value, green is going to be green value, and blue is blue value. Before we jump into the error, let's calculate the weighted color. Let's see. So first we need this arithmetic mean, but not arithmetic. We need a weighted arithmetic mean. So I have already searched for that. It pretty much tells you for all the values, sum it up, the value times its weight, and in our condition, like weight is actually the number of times, so the counter, and divided by sum of all the counters. So this is going to look something like this: 60/40 total 0 for size ti from 0 to 256 total. We're simply counting how many times we've seen all the color values for specific color, like for red, for green, for blue. Then we will have some float mean, and we loop through this same histogram again, and we're saying that, hey, mean plus equal histogram A times E. Finally, we're saying that, hey, mean, we need to divide by total. So this is exactly what we did in this formula. Right, so this counters time the value of the color, and then we divide by all non-zero counters. We will need to return a weighted color, which says that value is going to be mean, and we're pretty sure that because all the values are from 0 to 255, this float will fit our single byte value. And the error we haven't calculated yet. To do that, we will need a weighted standard deviation. Which is like calculated by, I don't know, like, we can open the same Wikipedia probably. Where was it? Over here. But yeah, it's a bit harder to read than in other sources. Let's see. Yeah, a bit harder to read. These are like way too mathematical notation. I think I saw a bit better, you know, something like this. So pretty much we're saying that no, somehow I don't like this formula too much. Yeah, here are the weights. Oh man. So this is square, yeah. This is square root. Alright, this is the formula I was looking for. Or maybe not. Oh god. Yeah, this is it. So what we need to do is we need to sum up the counters with difference between the color value and the mean or the average that we calculated, which is squared, and then we need to divide it by our total, which we already calculated. And in our case we can ignore this parameter because this formula is for deviation of a sample, but we are actually calculating for the whole population, and that part I think it's called Bessel standard deviation. It's Bessel correction, if I'm not mistaken. It's used in correcting the bias when calculating the deviation using the sample of the whole population. But as we're dealing with the box and calculate an average of the whole box, of the whole population, and we calculate the error for that. We don't need this param. It's also said that the higher the m value, the less impact it has. So how do we calculate it? We're saying that, hey, we have this variance 0. Again, we iterate over our histogram. We're saying that there is a diff, which is I minus our mean. Then our variance is actually the counter times diff. So this is this part, right? So this is diff squared. This is our counter, histogram at the index I, and this is summation, our for loop, where we sum it up. Then we can say that we need to divide it by our total. This is this part. Total is simply summation of all the counters. We skip this param because we don't need the bias correction. And finally, we need to take the square root. So we can say that, hey, the actual error is square root of our variance. Once again, this error is going to be used later on when we need to decide which quad is best to split. In today's episode, we are not going to be trying to find the best quad and simply split them one by one in a queue fashion. So now the thing is that we have calculated the average color for red, for green, and for blue, and each of those has its own error rate. And we would like to have a single value, so we need to convert it into like Grayscale format. So if we go to Wiki Grayscale and look at some information how the values, how much they contribute, we can see that red is 30%, green is almost 60%, and blue is only like 11%. So this is exactly what we're going to use. So let's say that our overall error is 299 times red error, then 0587 times green error, and the blue times blue error. So we convert from RGB into Grayscale and use and see like how much each color contributes to it, and this error rate then can be used to compare quads later on. So once this is done, our init method from single image is also complete, and we can now think what we can do when we need to split a quad. So first of all, we of course need to say that please allocate me some memory. And to do, we need some error checking that I won't do here right now. We just hope that enough memory is allocated always. And then we will return this children, but before returning, we need to say that, hey, top left is going to be some quad init, top right, bottom left, and bottom right. So what do we need to init our quad? We need to keep the same pointer to an image. So all the children quads will reference the same image as the parent quad, and every single quad need to do the same calculation as in this particular method, but instead of having this boundary, which is image boundaries, we need to split the parent quad into smaller quads. How do we do that? Let's see. Let's first define a function definition. So quad init, it will have a reference to an image. It will have left, right, width, and height. Right, some to do. Yeah, I can implement me. So that we see what we need to pass to this function here. So let's see. First, we need to calculate the middle points, the horizontal and vertical middle point. So let me show you, like mid, left, right is our quad boundary box. Okay, let me extract the box first, so that I don't need to type it out all the time. We need the midpoint, so we say box left plus box right minus box left divided by 2, and this is the correct way of finding a midpoint without overflow. We need to do the same thing for mid, top, bottom. So box top plus box bottom minus box top divided by 2. Now we have these two midpoints, and we need to now init the quad, our top left quad. So its left is going to be the same as parent quad left. Its right, not right, but its top. Its top is going to be the same as box top. Next, it's or is it? No, it's actually like left, right, top, and bottom. Yeah, let's do it this way. So let's think again. We start with left, and right is going to be the midpoint, mid, left, right. Top is same as box top, the parent top, and bottom is mid, top, bottom. Next one, this is top right, which starts with mid, left, right, ends with parent right, and it starts with top and mid, top, bottom. Next quad is bottom left. Its left is same as parent left. Its right is mid, left, right, because we split it. Its top is mid, top, bottom, and box bottom. Quad image, its bottom right, so its left is mid, left, right. Its right is parent's right, and again mid, top, bottom for top, and box bottom for bottom. Alright, so how do we implement quad init? And interestingly, I will just move it here. Interestingly enough, this is the implementation that we need. We can use left, top, right, and bottom right here. And when we want to init quad from image, we simply say that this is going to be quad init with image. Left is going to be 0, right? Next is right. It's going to be image width. Top is 0, and bottom is image height. And this is pretty much it for our initial quads. So let's jump back into main and see what we can do with it. Here we load our image, we need our context, and let's init our quad. So this is a root quad. We're saying quad init from image given our image. Let's now draw that quad. So instead of drawing the image, we're saying that, hey, let me draw the quad. So this is no longer needed, I think. We're still clearing the frame buffer. And then we need to draw the quad. So we're saying that from row is actually quad boundary box. Again, let's extract the box. Quad boundary box. So box top. Row is less than box bottom. Column starts at box left. Column is less than box right. We are saying that context frame buffer data equals to some color. Again, color is something that we already did before. Or quad average color red 16 quad average color. Should have extracted it, but let's go this way, finish it this way. Color blue. Again, where do we put it? We put it row times context frame buffer width plus column. I think that's about it. That's how we will draw our quad. Let's see. And from experience with this image, I believe this is the correct color. Right, so right now we have a single quad and it has squashed the whole image into its average color. The whole image is one simple color right now. This is absolutely not interesting, and we would like to start splitting the quad into smaller quads. Now to do that, we need to keep the quads somewhere in some sort of queue, and the easiest way to do that is to use some dynamic array, which is once again can be achieved by using this STB repository with header only dynamic arrays, which is stb.s. Let's create stb.s header file, paste. Oops. We need to copy this whole contents, paste it here. We also need this flag, so we create stb.dsc include stb.ds. So once again, this is simply a workaround for LSP to work with it correctly. Let's get back to main. We can include it here. We can say that we're gonna have queue. We're gonna have a queue of pointers to quads, and our first root quad we're gonna push to our queue. And instead of drawing a single quad, we are gonna pass queue to our draw image. So this is going to be actually queue. Now queue contains many quads, so we can say that, hey, for size ti from 0, I is less than q length. We're gonna grab our quad from this q by the index. And draw it. Thing is that we need this q length, which is our length of q. So this comes from the same stdds. And this whole thing says that, hey, give me the length of the array, which is named q, and for every single quad inside this q, please render it. Okay, it says, what was it? Passing quad, const quad. Okay, let's just drop this const for now. No, it should be fine. And nothing really changed, but instead of drawing a single quad here, we're actually going over the whole queue. And now that we have this queue, we can start splitting the quads and put its children into the queue. We can do that here in our main loop. We can check that if event type is SDL event key down. So on any key press, we can call our quad split. Yep. Quad split, but which quad? And it is going to return some children. And here it's going to be some quad. Where do we take quad? We need to take quad from the queue, and we need to access it by some index. Queue index. So we're going to say that hey, queue index start at 0. We put the root. Currently queue index is pointing at the root, and once we pull it out of the queue, we need to say that hey, we no longer want to ever split it again. So we move the index +1. We split our quad. We need to push all the children top left into our queue. It wants pointers. Top right, bottom left, and bottom right. And the only thing here is that this won't, no, this could work, but really we need to also pass this index into our draw image so that we know that if the quad has been split, we can ignore it. Maybe one thing here is that we can say that it needs to be quad children, right? So we assign it. Yeah, I guess we can do it this way. And now, not the quad. Oh man, jumping too much. This is, oh my god, what is up with my keystrokes? This is queue index, and instead of starting with 0, we will start with queue index. So queue index represents a point in this queue or in this array, which points to the quads that haven't been split yet. And once I press a button, we pick the next quad, we split it, we make sure that we point to the next queue or to the next quad in the queue. We push all the children, and let's see what it does to our all picture. So this is our root quad. Now I'm pressing a button on my keyboard. We see 4 quads, and now we go from one to the next, and I'm pressing like a lot. And we can see that our owl picture is there. The problem is that I have the button pressed down, but it's kind of slow. We can increase the speed. For example, whenever I press down a button, I can say that, hey, for I from 0 up to, let's say, 50. Right, so I'm gonna split 50 quads. So this changes the picture in a faster way. Let's get back to, say, let's do 10 or something. Let's run it. And the thing is, sometimes when it does some splits in this area, it is not really visible to us. And what we would like to do is to have those borders that are shown here in the final result. Let's try to do that. To achieve it, what we need to do is we need to say that, hey, let's initialize our context and create both window, texture, and frame buffer with a bit bigger width and height. And then when we draw, right, we can say that, okay, our some sort of padding is going to be 1. And when we are drawing the quad, maybe not when we're drawing it, maybe when we're splitting the quad, top left, no, actually, where do we want to do that? Probably here. So if we start with top with padding, we apply the padding. When we draw the quads, no, that doesn't work right. All right, let me see. All right, let's redo this whole thing a bit, because this thing and this thing, they're doing somewhat the same stuff, and we can simplify it and then make the whole padding and border work. So let's extract it as draw rectangle. So given some STL context, I want to draw something from left and top, given some width and given some height, right? So I want, and of course I need some color. So if we pick this for loop, we're gonna say the row is going to be from top. It's going to be less than top plus height. Column is from left, less than left plus width. And then, yeah, we don't need the whole context. We can say that, hey, I need the frame buffer only here. So frame buffer, we set the color. So this is like a generic draw rectangle function. Given the left and top corner coordinates, given the width and height of the rectangle, make it the whole rectangle with this color. So how do we clear it? We're saying draw rectangle context frame buffer, left is 0, top is 0, width is context frame buffer width, height is context frame buffer height, color is black. And then when we draw the quad, we have the box. So we're gonna say that we're gonna say draw rectangle. We need the frame buffer. Then left is going to be box left, top is going to be box top, but we're gonna apply this padding for the border. Then it's going to be the width is right minus left minus padding, and height is going to be bottom minus top minus padding. You can drop this, and the color is going to be some color. And I deleted it. I think color is right here. Color. Comma. Let's see whether that fixed our issue with the border, and it did. So right now, whenever we do these quad splits, we can see exactly which quads are being split. Right, so let me restart it again. Let's go back and do this splitting here. Instead of 10, let's go 1 by 1. We can now run it. All right, so as you can see, we're simply doing it in a queue style, so whoever came first receives the first split. And in this area, we don't really need the split, right? Because these colors don't change that much compared to this area where the owl is. It has a lot of gray details for the owl, so it makes sense to split this area before splitting these background colors. To achieve that, we need some sort of prioritization system. In other words, we need a priority queue instead of a simple array or a simple queue. That is why our quads that we calculated in our quad H has the error. So the higher the error, the more important the quad is for splitting, and it also has the area. So the bigger the area also affects whether we need to split it before other quads. And that is what we're gonna do next time in the final episode. I hope you like this content, and if you do, please like this video, subscribe to the channel, and I'll see you again. Thank you.